Radians also give us a nice way of measuring what are called sectors in circles. So in this circle here I've shaded in blue this region. A region like this that kind of looks like a piece of pizza is what we call a sector of the circle. And there is a strong relationship between the angle in radians and the area of one of these sectors as well. If we have a look here, again I've got the unit circle to start with. And if you have a look at the area compared to the angle at the center, you should see that the area seems to be half of that angle. Okay, so that's the deal with the unit circle. It gets a little bit harder to see what's happening as we change the size of the circle. So let's make this 2. There's not really an obvious relationship necessarily. In this case, okay, all of a sudden this thing now has an area twice the angle at the center. If I bump this up to 3, though it's not 3 times the area, it's some other relationship that's going on here. Now the relationship between these two can be worked out. And the way that we're going to work that out is to compare the properties of this sector with the properties of the whole circle. So let's think about each of those things. Let's first of all think about the sector. Okay. Well, the angle that's at the center, theta, that's what we call it. So we have an angle theta. And we're going to call this sector area with a little s subscript here. So that stands for area of the sector. So area AS. Now let's compare those with the full circle. So in a full circle we have an angle of 2 pi radians. We know that from our work earlier. And we have an area, if you remember, back to high school, we would use the letter A to represent an area. Here we've already used an A with a subscript S, so I'm going to call this AC for area of circle, equal to pi r squared. Now, a sector is just a fraction of a full circle, and we're going to use that property to work out the area of this sector. Okay, so what we can do is we can work out what fraction of the circle we're dealing with here. To do that we can use the angles. Okay, so we've got theta radians, how big this angle is, out of a maximum of 2 pi of them. And the sector that we've got has an area AS, which is a fraction of the circle, AS out of a full pi r squared. That would be the maximum size. So these two fractions should be the same, which is why we can set them equal to each other. And now it's just a matter of tidying up. What I'm going to do is I'm going to multiply both sides by this pi r squared so that I get theta on 2 pi times pi r squared equals AS. So the area of a sector is equal to, tidying up this left hand side here, that pi and that pi are going to cancel, and I'll just rearrange that to make it look a bit nicer. It's going to be a half r squared theta, and this is the area of a sector in a full circle. Okay, and this kind of makes sense if we think about those examples we had before. Okay, when we had r equal to 1, okay, using this formula here, we would get that the area of the sector was a half times 1 squared theta, which is a half. The 1 squared is still just 1 half of theta. So this was saying that when we had that radius of 1, we noticed that the angle, if you divided the angle by 2, you got the area of the sector. The area of the sector was half the angle. Okay. Similarly, when we went to r equals 2, we would get this, half times 2 squared theta. 2 squared is 4, half of 4 theta. Half of 4 theta is 2 theta. So in that case, we had that the area of the sector was twice the angle at the center, and so on. So this allows us to get get the area of a sector with a given angle at the center. And it's a very, very powerful formula. So that is one that you need to make sure you record, because it is a formula that we're going to keep using from this point on.